Hello students, in this video we'll talk about path independence. We say that a vector field is path independent or has the path independent property if the integral over C1 of v dot t hat ds is equal to the integral over C2 of v dot t hat ds, as long as C1 and C2 start and end at the same points, as long as and C2 have the same initial and terminal value. Okay. In other words, if I have a vector field, and let's just look at it in two dimensions here. Here's my vector field. There's a vector field. There's the x-axis. There's the y-axis. And if I compute the flow, so if I have this point over here P1 and this point over here P2, a vector field is path independent if it doesn't matter which way I go to P1 to P2. So I could go this way from P1 to P2, and that can compute the flow. It'd be exactly the same if I went from P1 to P2 along this other wacky curve over here, right? It would be exactly the same since I start and end at the same point. It doesn't matter which point I start and end at. That's what path independence is. So it's independent of the path. Now, it turns out that if you're independent of the path, it turns out that V must be conservative, must be a gradient vector field. So path independence is true if and only if V is the gradient of some scalar function phi for some function. Phi. Now, how can we see this? One direction is clear. If you are a gradient, then these flows will simplify. So for gradient vector fields, the integral over C1 of v dot t hat ds is the integral over C1 of gradient phi dot t hat ds, which by the fundamental theorem is going to be phi of the terminal point P2 minus phi of the initial point P1. It didn't matter what curve I picked. It only depends on the initial and terminal points. So it's path independent. So in other words, if you are a gradient, then you're path independent. Now, the other direction is a little more interesting because if we happen to be path independent, we want to show that you are a gradient. So if you're path independent, if V is path independent, then I can say that V, I can define a function phi. So what will phi be? Then phi of x, y, z, which is the integral from x0, y0, z0, any fixed point you want in space, one fixed point, so this is fixed, to x, y, z of v dot t hat ds will be the potential function. And how can we see that? Well, what we can do is we can note this. We can look at the difference phi of x plus h comma y comma z minus phi of x, y, z. Let's think about what this would be. Let's write down the two integrals. This is going to be the integral from x0, y0, z0 to x plus h, y, and then z v dot t hat ds minus the integral from x0, y0, z0 to x, y, z v dot t hat ds. What this will turn into, so in other words, if you're going to start, so what does our curve situation look like? If we go from over here, we go to this point x, y, z, and then I can go to the point x plus h, y, z. and shift just the x over. So what will happen is this is going to turn into the integral from x, y, z to x plus h, y, z, then v dot t hat ds. So if I divide this by h over here, and I divide this by h over here, what I have is I can do any path I want. The only thing that's changing is the what? The only thing that's changing in this integral over here is the x. The x is the only thing that's changing. So by the fundamental theorem of calculus, as h goes to 0, this is going to turn into just the first component of v. That's the only thing that's going to be changing in here. So you're going to have the component of v, which is going to be, so partial phi partial x is going to be what? This limit over here tends to v1, the first component of the curve, as h goes to 0 by the fundamental theorem of calculus, because the only thing changing here is the x direction. Everything else is fixed, so the v2 and the v3 components, when you do the dot t hat, because remember, what's the t hat going to focus on? The t hat is just going to focus on the what component? The t hat is just going to focus on the x component, because that's the only thing changing. So the unit tangent vector that direction is only in the v1 component. So as h goes to 0, this tends to v1, and therefore partial, as h goes to 0, this will tend to phi x. So phi x is equal to v1. Similarly, phi y is equal to v2, and phi z is equal to v3. So this function over here, which is well defined by path independence, is going to be the scalar potential of the vector field v if v is path independent. Thank you very much.